All right, my AB kids, we are on section 6.8, indefinite integrals, versus section 6.7 that was definite integrals. What's the difference, you say? And I say it's all about the bounds. It's all about the bounds. All right, so in the beginning here, they're trying to, we talked about this in the last section, so they're just kind of reiterating this fact and giving you more explanation about the C value that we talked about. So find the derivative of each of these. All right, we can find derivatives. Check me out, power rule. Power comes down in front, take it to 1 less power. Power comes down in front, take it to 1 less power. Power comes down in front, take it to 1 less power. But you have, see how this one has a +1? This one has a -5. This one has a +1,000. Why are we not considering those as part of our derivative? And the answer is because the derivative of a constant is 0. All right, and also you can think about it this way. If I look at this particular graph, x squared plus 1, you know that that's a happy parabola moved up 1. This one's a happy parabola moved down 5. This one's a happy parabola moved up 1,000. So they're all the same happy parabola in the end, but they all have a different vertical shift to them. So what is the antiderivative of 2x? It is x squared plus c. And we know that because remember, we take, if I were to take this, the integral antiderivative of 2x dx, you would add a power on, 2x squared, divide by that power. If I add a power on, divide by the power, they cancel. And then I get an x squared. So I get that function, x squared plus c. There's a solution. This one's called the general. This is really going to be important to our lesson today. This guy's called the general solution. Because what you're saying is, you know it's x squared, but you don't know vertically where it is. It's a general solution. Not specific. Could be up 1,000, could be down 5, could be anywhere in between. It's a general solution. This one here, if I look at this one, he's called a particular, I guess I should have put it over here in front. I didn't realize that. General solution. This one's called a particular solution because now you know specifically where it is. So this one, because it's the general solutions are the plus c's. This one's a particular solution when you're actually able to figure out what that number should be. So we're going to see some problems today where they're going to give us enough information for us to be able to figure out what the particular solution is, what the real actual solution is. And so integrals without a boundary are called indefinite integrals. Indefinite integrals. Integrals without boundaries. These are the guys that need the plus c because there's no boundaries on it. So indefinite integrals need that plus c. That's really important. In the past, we've been working with definite integrals where the boundaries are given for the area under the curve. Now we're going to look at indefinite integrals, which means we're finding an antiderivative as a general solution. So they're going to remind us of some of our derivative rules. So if you go to your note cards where you have them all written down, e to the x is the best. He's the best function ever when it comes to calculus because his derivative and antiderivative, his derivative and his integral are all the same thing. So this guy would be e to the x plus c. If you have a, meaning like 3 to the x power, some kind of constant to the x power, a to the x, when you take the integral of that to undo it, it's 1 over the ln of a times a to the x, and then a plus c. So they give you a couple examples using this. Find the general solution. General solution's the guy that's going to be plus c of 7 to the x. Well, that's this situation, right? So if I want to figure out what the integral is, or capital F of x the antiderivative, the integral, they're one and the same thing. If I want to know what capital F of x is, I'm using this rule. It is 1 over the ln of 7 times 7 to the x plus c. Easy enough when you have the rules in front of you, right? All right, if the derivative is e to the x minus 2x squared, find a particular solution if f of 0 is 4. So this one's not going to be a plus c because when it's a particular solution, you don't need, they're going to give you, they gave you this extra information so that you can find what c actually is. So let me show you. The beginning of this is going to be the same as actually not going to be the same. This one they gave us, they gave us the derivative and we want to go back to the function. I want to know what f of x is. So that means that f of x is the integral of e to the x minus 2x squared with respect to x. And so I antiderivative it. So antiderivative of e to the x is e to the x. 2x squared, it's going to be 2x, one more power, over that power, plus c, right? But then they gave me information, and this information here says that when my function has an x value of 0, the y value is 4. This is your x, and this is your y. So, and remember that you're looking at what this function is. So this is going to be, we're just plugging it in. 4 is my y, here it is, equals e to the 0 minus 2 times 0 cubed over 3, my x is 0, plus c. And from that, you're going to be able to figure out what the actual c value is. And so if I do that, I get 4 equals e to the 0 is 1, minus this whole term zeroes out, plus c. If I swing the 1 over to the other side, I end up with 3, so I get a c that equals 3, which means that I can go back to this equation up here. I think I might put it in red. Back to the antiderivative equation and plug in the fact that you know that c actually is 3. So my final best answer for this guy is e to the x minus 2x cubed over 3 plus my c value that I was able to actually calculate out, and that's 3. And that's what the actual function is. Okay, so when they give you the extra information, you can figure out what the particular solution would be for this equation. This one, they didn't give you enough information. You just needed to figure out the general equation. Okay, another reminder of derivatives and integrals. If you are 1 over x, think about what function generates that as its derivative. And that would be the natural log function. So it's the natural log. They always use absolute values with this. Absolute values for that. So anytime you have a natural log as part of your function, it's going to be with absolute values in the midst. Because you know that logarithms, I'll make note of it, logs can't be negative. And since they can't be negative, they just use those absolute values to get around that. I don't know if you remember like what the logarithm graph looks like, but if I go just slightly over to my margin so you can see. Logarithm graphs come up the y-axis asymptoting it and then go off to the right. So you'll see you never have an x value that's negative. Logs can't be negative. They never go that way. They won't cross over that y-axis. Okay, so the next one, number 3. They're trying to remind you of logarithms. This would be, there's a couple different ways I can write it, but let me start out with this. The integral of 1 minus 5x to the negative 1 power. That would be the same thing, right? As 5 over x. So if I apply my power rule to it, this one has an x to the 0, so one more power on gives me just an x. I'm looking for my capital F of x, my antiderivative. That would be an x for the 1. Then I end up in a jam here because if I go to one more power, I would have 5x to the 0 power, and that's just not going to work. So really this thing is the same as 5 times 1 over x. Maybe I could look at it that way. So if that's the case, then I have, and it's a negative subtraction, I have 5 is like a coefficient, and what's the antiderivative of 1 over x? It's the ln of x plus c. And that's my answer for that. That just to find the general solution. They didn't give me enough information for me to find the particular solution, but number 4 does. Number 4 does. And so what I want to do is figure out what the original function was, and then I'm going to plug in the fact that x is 1 and y is -7, and that's going to let me figure out what c is, so I can find a particular solution, the exact solution for this one. All right, so I'm trying to find f of x, and f of x is the same thing as capital F of x in this case because they gave me the derivative and I'm going backwards. If I have 2 over x, same thing like this guy, right? What's the integral of 5 over x? 5 natural log of c. Well, what's the integral of 2 over x? Well, it's 2 natural log of x. I meant over there. So 2 natural log of x. This guy here is 6x to the -2. Maybe I'll put it over here in the margin. 6x to the -2. So I'm going to have plus 6. I have to add a power on, -1 over -1, and then a plus c. So before I plug in my 1 and 7 for my x's and y's, let me just simplify this a little bit, make my math a little bit easier. So 2 ln of x minus 6, I'm going to put it over x, and then a plus c. And I know from the coordinate that they gave me, this is a coordinate that's on the actual function, that when y is -7, x is 1. 2 ln, I'm replacing my x's with 1's. And I'm going to look for what c is. What's the natural log of 1? What power generates an answer of 1? And that would be 0. So this whole thing is 0. So I've got -7 equals 0 minus 6, 6 over 1, plus c. So I'm looking for what c is. I'm going to flip things around here. C equals, if I add 6, I get -1. Which means that my original function, I'm out of space. All right, here we go. My original function must have been, go back to the function here, we're going to replace our c with a -1. So I have 2 ln of x minus 6 over x minus 1. And that's my particular solution. So there's number 4. Let's see if there's more examples. Yeah, a few more. There's a reminder, I think in the last section, that we did sine and cosine already for this. Again, the integrals for sine and cosine, they were in our last set of notes, but he put all 6 together in this list, so that's cool. So you have a spot to look. This is the sine of x plus c. This one's a negative cosine of x plus c. This guy, secant squared, whose derivative is secant squared, that's tangent. Whose derivative is cosecant cotangent, that would be negative cosecant. If I'm looking at secant tangent, that's secant's derivative. And cosecant squared is negative cotangent. So reminders of those, we're going to be flip-flopping back and forth. It's just going backwards on your card. If you have cards for derivatives that we made, you're going looking at it the other way. You're going right to left instead of left to right. All right, so this one's super duper easy. Antiderivative, capital F of x, is going to be 3, whose derivative is secant squared. Your integral of secant squared is tangent, so this is going to be 3 tangent of x plus c. Then they might have a particular solution guide, right? Particular solution, we're going to just figure out what the capital F of x is. For a 1 minus sine, well, the antiderivative of a 1 is x, and minus the antiderivative of sine is negative cosine, so make it plus cosine, plus c. But they gave you enough information to figure out what c is. When x is pi, y is pi over 2. All right, plug it in. Pi over 2 equals pi plus the cosine of pi plus c. And supposedly we should be able to figure out what c actually is like we did in the others. Can't mess with a pi minus 2. They are pi minus 2. This is a pi. Cosine of pi, though, we can play with. Cosine of pi is negative 1. If you're at pi, the x value is negative 1. All right, let's put things together. If I subtract pi, the pi's cancel out. If I bring this negative 1 over here, it becomes negative 2 plus 1, or negative 1. So I get a c value that's negative 1, and now I can put my function together. Antiderivative is x plus cosine of x minus 1. Then there's a reminder for these inverse trig guys. This is going to come up a lot in the next section, that you need to remember these inverse trig ones and what they look like. So it's kind of a good reminder for them. The inverse sine. Remember, anytime it's an inverse trig function, it's the same thing as saying arc. And then, like, this one would be arc sine. They're one and the same thing. They're the same verbiage, just written a different way. This would be arc secant. This would be arc tangent. You're allowed to use that word arc to signify that it's an inverse trig function. So you might see it one way written this way, or you could see it as an arc sine. They mean the same thing. So here's what the inverse sine derivative is. Now we're going derivativing. It would be 1 over, these are the ones that you had from previously, square root of 1 minus x squared. And notice these are derivatives rather than integrals that were on the last page. If the secant guy, secant to the negative 1, he is 1 over the absolute value of x times the square root of x squared minus 1. And the derivative of inverse tangent is 1 over 1 plus x squared. You could also see that as 1 over x squared plus 1. Either way, they're the same thing. So then let's take it to integrals, which is what we're into now. Whose integral is 1 over the square root of 1 minus x squared? Remember, you're reading it right to left, so you're going to say sine to the negative 1 of x plus c. And again, you could see that as arc sine of x plus c. Whose integral? The integral of this, well, going right to left, is secant to the negative 1 plus c. All right, I believe these are the last two. They are. And then we just have a couple examples to go through. So one of the times when you're looking at this, you're like, whoa, Nellie, I have not seen an integral like that before. That looks like a whole hot mess. How am I supposed to undo a hody high, right? Because this is a fraction. So sometimes it's easier for you. It depends on the problem. Sometimes you can just divide, especially when it's a single denominator. Like this is a single term, a monomial. A single term denominator, you can just divide each piece individually. So in other words, you could say for this thing, you're going to divide by x is your big deal here. Divide by x, and here's what it's going to look like. You'll have the integral of 3x squared over x plus x over x minus 2 over x, right? And all of that is with respect to x. It's exactly the same thing, You're just writing it a little differently. And the reason you're doing that is because now you can simplify it. 3x squared over x is 3x. X squared over x is 1. 2 over x stays 2 over x. And then you can integrate each piece. So the power rule, apply the power rule to that. Add a power on, divide by the power. This would be a 3x, one more power, divide by the power. Add a power on. Well, there's no x. X to the 0. 0 plus 1 is 1. This is just an x. 2 over x. We saw that in one of the earlier problems today. If you have that situation, it's an ln, so minus 2 ln of the absolute value of x plus c. Did they give you enough information for you to be able to do a particular solution? And they did not. So you're done. So sometimes if you have a single denominator, try to divide them out. Makes your life a whole lot easier. Sometimes you might need to distribute, and that's what this guy's about. This one here is like x to the 1/2 power, right? Square root. So before you even integrate, before you even go for finding your capital F of x, we're going to distribute this 3x to each of these guys. Okay, so 3x to the first times x to the 1/2. What do you do with the exponents? We add them up. So 1 plus 1/2 is 3/2. There you go. We've distributed the first one. 3x times x squared is 3x cubed. All right, so go for capital F of x. Add a power on. I have a 3 there. Add a power on. 5/2 divided by 5/2. Remember what happens with the fractions? We saw this previously. If I'm dividing by 5/2, I'm really multiplying by 2/5. So it's going to be times 2/5 x to the 5/2 power. Add a power on, divide by the power. Dividing by the power means you're going to have to multiply by the reciprocal. Whew, plus 3, the coefficient. Add a power on, x to the 4th over 4 plus c, and then pretty it up. So I have 6/5 x to the 5/2 plus 3/4 x to the 4th plus c. Best I got. Okay. We're going to do a few practice problems together, just a few, and then call it a day for this one. This next one I want to do is number 6. And the reason why I chose number 6 is, again, sometimes you have to manipulate things a little bit before you actually take the integral to find capital F of x. As I look through this, like this one here, t to the 1/2, you're going to distribute that just like we did in that very last problem. This one you're going to divide everybody by x, just like we did previously. So, this one here is going to be multiply these together, x to the 1st, x to the 1/3. All right, so you've got to manipulate them algebraically a little bit before you even try finding your capital F of x, the antiderivative. But how about number 6? What would you do in number 6? The first thing that I would do is think the integral of, square it out. 3 minus x times 3 minus x gives you a quantity 9. Now you're just totally foiling. Minus 6x plus x squared with respect to x. And then you're ready to find the integral for this guy. So if I do that, 9, add a power on, 9x. 6x, so minus 6x, add a power on, divide by the power. X squared, add a power on, divide by the power, plus c. Can I make it any better? And the answer is 9x minus 3x squared plus. Sometimes you'll see this written as 1/3 x cubed. You could also put this as x cubed over 3. That's the same thing. And then, just noticing mistake on my answer key. And then you're going to take the plus c. I have this as being minus, but I believe that it really should be plus. So let me look at it one more time. When you FOIL this back, 3 minus x times 3 minus x, this guy is negative x times negative x, positive x squared. So we are correct on what we just did. I will correct the homework guy. All right, number 11 is next that I chose. Number 11, who's got the derivative of cosecant cotangent? We've got a 3 from the coefficient here. It would be cosecant cotangent. You can go back to the list that we created just a couple minutes ago on the other page. It is negative cosecant. So negative cosecant of x. The antiderivative of a 1 is minus x, and then a plus c, and you're done. If I go to 16 as my next one, 16 was my next choice because, of course, it's got trig functions, and I know you always pick those for me. Find the function that satisfies the given conditions. So now they're giving enough information where you can find the particular solution, and you do not need a plus c at the end. But your process is going to be the same. So I want to know what the function is. If they're calling it dy over dx, I'm going to call my function y, and I'm going to apply the power rule to this. So I have 2x squared over 2. The integral of sine is a negative cosine, and I have a plus c initially. I know my x is 0 and my y is 4. Now, by the way, these two's canceled out. So 4, my y, equals 0 squared minus the cosine of 0 plus c. Cosine of 0 is the coordinate 1, 0, so this is a 1. So I have 0 minus 1 plus c. Take your negative 1, add it to the other side, I get 5 is my c. And so I know that my function would be y equals x squared minus cosine of x plus 5. There's 16. Last one that we're doing together, and that is number 18. Because they gave us some crazy information this time. We're going to have to go a couple different steps. Because look at this, second derivative. They gave me the second derivative, and I'm trying to get to the function. So watch how this one goes. It's kind of cool. The process is the same. I'm going backwards a step. I'm taking a step back. So that means that I want to go, I need to use the integral. I want to go from the second derivative to the first derivative. That's job number 1. So that just means take the integral of sine of x. Well, the integral of sine of x is a negative cosine of x, like we've seen, plus c. In order for me to ultimately get to the original function, I'm going to have to go backwards again. But before I go there, I have enough information from this fact to be able to solve for c, so that I can be very specific on what the original function was. So if I plug in, I know that my x is 0, my y is 1. 1 equals a negative cosine of 0 plus c. That's coming from here. Y is 1, x is 0. All right, cosine of 0 hasn't changed. If I go to 0, it's the coordinate 1, 0. X value this time, cosine. So 1 equals negative 1. Cosine of 0 is 1, but the negative in front makes it negative 1 plus c. When I join my 1's up, I get c is 2. So here's my actual first derivative for real, based off the information they gave me. Negative cosine of x plus 2. But I need to go back to the original function. So now I need to do the whole process all over again. I'm going to take the integral, or capital F of x, the antiderivative, however you want to say it, of negative cosine of x. So I'm looking to get to the function, what the actual function is. So I'm taking the integral of this. Negative cosine would be negative sine. The integral of 2 is 2x plus c. But lo and behold, they gave me information enough right here for me to be able to figure out what this c value is. If x is 0, y is 6. Let's try it. 6 equals the negative sine of 0 plus 2 times 0 plus c. So it all really hinges on what's the sine of 0. Sine of 0 coordinate is 1, 0. Sine's the y coordinate, which is 0. So this is 0. This is 0, which means that c is 6. And if c equals 6, then I can tell you exactly what my function is. The function is negative sine of x plus 2x plus 6. All right, that takes care of section 6.8 on indefinite integrals. Shoot me an email if you've got any questions, and I will see you in class.